Okay, so this is kind of a help session, I guess, for Module 5, which is basically just synchronous machines. So here's the only equations that you need to know, and I'll go over them. So basically, in a synchronous machine, to make the equivalent circuit, it is going to be an open circuit, as seen here and as seen here. So more or less, there's two ways to read this open circuit. There is the motor reference, which basically means you're reading it from the motor side, which is VA. That's why IA is going down that way. Then you have the generator reference, which the generator in this case is EAF, where IA is going to the right. So you have to understand what the question's asking, first off. And second off, you just have to be able to apply. So here's the three equations that you're going to need to know. Remember, technically two, but we have EAF equals 1 over the square root of 2 times omega E times LAF times IF, where EAF is going to be the generator voltage. This 1 over the square root of 2 is just going to be your RMS conversion. Omega E is equal to 2 pi F. Let me write that down. LAF is usually given, but he might ask you to solve that. And IF is going to be your field current. And keep in mind, this is from getting your open circuit voltage. Then your two EAFs for your motor and your generator. Basically, you just do KVL. I mean, it's simple stuff. So for the motor, it would be, plus VA minus EAF, and then minus IA times whatever is in here, and the complete opposite for the generator. So, enough of me yapping up a storm. Let me actually do a question. So, example 1.5. It says a 60 hertz three-phase synchronous motor is observed to have a terminal voltage of 460 volts line to line and a terminal current of 120 amps at a power factor of 0.95 lagging. The field current under this operation condition is 47 amps. The machine synchronous reactance is equal to 1.68 ohms per unit on a 460 volt 100 kilovolt or kVA three-phase base. I can't read. Assume the armature resistance to be negligible. So basically, we already know the R is going to be 0 because it's negligible. So like I said earlier, you have to find out if it's a generator reference or it's a motor reference to determine your IA. Now he has it here, but I'm going to teach you how to exactly look at it. So it says a three-phase synchronous motor is observed. So you already know we're observing it from the motor. So we'll get to our 2, and then we'll realize we're going to be using the motor open circuit, not the generator. So this is what we're going to be following, where this is our A, and this is JXS. So now that we know that, let's write down what we got. So we got F equals 60 hertz. We have that V line to line equals 460 volts. We have that the terminal current is 120 amps. That's going to mean IA is going to equal 120 amps. And that we know that the power factor equals 0.95 lagging, which is important. And we know that IF is going to equal 47 amps. Alrighty. So, you guys can pause the video, but I'll just get into it. So, more or less, it's asking us to calculate the generator voltage, EAF, in volts. Like I said earlier, it's just your simple, KVL. So it'd be minus EAF plus, well, actually not plus in this case, it'd be minus IA phase times Z total, which is just going to be JXS. I'll put Z total. Plus VA is going to equal 0. On the page. Okay, So moving stuff around, you get EAF is equal to negative, oops, I'll write it this way actually, VA minus IA phase times Z total, which is RA plus JXS. But we already know RA is going to be 0, but I wrote it down anyway. Okay, so, basically what we need to do is we need to solve for EAF. So EAF equals, now we know that VA, which is our reference, by the way, I should have mentioned that earlier, so it's always going to have phase 0 degrees. We know that our line to line is 460 volts, but in this specific equation, it's not asking for line to line. VA is the phase, or line to neutral. So we're just going to do that VA, or that V line to line, which is 460, and divide that by the square root of 3. Okay, minus IA, we already have, is 120 amps. So now we have to find the angle, or the phase angle. But good thing that we have the power factor. So we know that 0.95 equals cosine of the angle, and the angle is going to equal cosine inverse of 0.95, which is going to equal 18.19, but we know it's lagging, so it's going to be a negative 18.19 degrees. Multiplied by 0 plus JXS, where we know that XS is, I didn't write it down, is 1.68. So you all have calculators, you could calculate this, but so we are going to get 278.83 phase negative 43.38 degrees as our EAF. So that satisfies our first question in our problem. Now it's asking for the magnitude of field to armature mutual inductance LAF, which is part B. So what other equation did you know I give you guys? Well, that is, we'll go back to the set of equations, and we'll look at the two that we already didn't look at. This right here. So what do we have? We have EAF, omega E equals 2 pi f, which we have. We don't have LAF, and we have IF. And it's asking, to find the mutual inductance LAF. So we have everything to solve that. So rearranging that equation, we're going to get EAF times the square root of 2 over omega E times IF. So notice how it doesn't have the little caret on top. That's just saying that it just wants the magnitude. It's going to be 278.83 multiplied by the square root of 2 over omega E, which is 2 pi times 60, because that's what F is. And then IF from above is 47. So your LIF is going to be 0.2225 henries, or LAF is going to equal 22.25 millihenries. All right, so that solves your second one. Now on to the third one. It says it wants the electrical power input to the motor in kilowatts and in horsepower. All right, so it just wants P in. I mean, simple, right? So we know that P in equals 3 multiplied by V phase times I times the power factor. We have everything for this now. So P in equals 3 times 460 over the square root of 3 times our I, which we already know is 120. Also times our power factor, which we know is 0.95. So P in is going to equal 90,828.74 watts. So that's in watts. The question also asks, well, it asks for kilowatts actually, so that would just be 90.8 kilowatts. You'll see why I kept it in watts in a second. It's also asking for the horsepower. Well, the equation for horsepower is 1 horsepower equals 745.7 watts. So basically, we're going to take our 90,828.74, divide that by 745.7 watts, and that's going to give us 121.8 horsepower. So to recap the first example, we figured out what reference we had to look at, which was a motor. We wrote down what we knew, and then we used KVL to come up with the equation. So we solved for EAF. We used our open circuit voltage equation to solve for LAF, and then we used our Pin, which we already know, to solve for the total input power, and then we converted our power from kilowatts to horsepower. So now I'm just going to do the homework question. I'm just going to do part A for each because it's just asking it all three different power factors, which is really simple. I mean, you just change the power factor, it's the same thing. So you guys could do that on your own time. So first, let's read a 575 volt, 50 kilowatt, 60 phase, 3-phase synchronous motor. Remember, 3-phase synchronous motor. So we already know that we're reading it at the motor reference. Has a synchronous reactance of XS equals 4.65 ohms. And an armature to field mutual inductance LAF of 105 millihenries. The motor is operating at a rated speed and terminal voltage and an output power of 40 kilowatts. Ignoring losses in the motor, which we saw that before, calculate the magnitude and phase angle of the line to neutral generated voltage EAF and the field current IF if the motor is operating at, well, we're just going to do A, 0.9 power factor lagging. So we'll write down what we know. We know V line to line equals 575 volts. We know F equals 60 hertz. We know we're reading it as a motor reference. We know that XS equals 4.65 ohms. We know that R is 0. And we know LAF equals 105 millihenries. And we know P out equals 40 kilowatts. So going back to what I was saying before, it is crucial that you guys either write these down on your formula sheet or know them. That's how you're going to determine your EAF, is dependent on your IA current. So, you know, it's positive or negative depending on. So we know it's a motor reference. We're going to be using the first. So, I mean, you could either memorize the equation if you don't want to write it, because it's going to be the same equation every time. But I mean, realistically, the KVL is so simple to the point where you don't really, you know, need to memorize it as long as you write it down. But we just are gonna know EAF is just gonna equal VA minus IA phase angle multiplied by Z total. Okay, so we have VA. We know that. Well, VA is going to equal VLL over the square root of 3. You just have to do that quick conversion. We don't have IA. We do have the angle, though, because we know the power factor equals 0.9 lagging. So cosine inverse of 0.9 is going to equal the angle. The angle is going to be negative 25.84 degrees, because the current lags the voltage, so it's going to have to be negative. So we got that. Sorry, I got to add another page. And Z total, we know, equal RA plus JXS, which is just going to equal JXS, which we know is going to be J 4.65 ohms. So how are we going to find I? Well, we have to look at what we know. We know power, and we know the voltage. We know the power factor. We could find I. So we use the equation. P out is going to equal 3 times V phase times I times the power factor. Rearranging that, we're going to get I is equal to P out over 3 times V phase times the power factor. So I is going to equal, the power is 40,000 watts over 3 times V phase, which is going to be V line to line, which is 575 over the square root of 3. And we're going to multiply that by the power factor, which we know is 0.9. So our I is going to equal 44.626 amps. So now we want to plug that into our original equation. So EAF is going to equal 575 divided by the square root of 3 minus 44.626, the angle of that we found earlier, negative 25.84 degrees. Multiply that by Z total, which is just JXS, which we know is J of 4.65. So now that we know that, EAF is going to be 575 So equal 305.3 phase of negative 37.7 degrees. I'm just going to make sure my calculations are right. So we solved part A of the problem. Part B, or sorry, the second part of the problem is asking for IF. So, going back to the same equation earlier of the open circuit, we know that 1 over the square root of 2 times omega E times LAF times IF. So, we have, EAF, we have omega E, and we have LAF. So, rearranging again, we get basically, that's just going to be, like I said, the magnitude and then LAF equals 105, but it's millihenries, so we want to convert that to henries within our equation so we could get a nice clean amps. So our IF is going to yield 10.91 amps. And there, you just solved part A. All part B is asking of you guys is to just change the power factor. So all changing the power factor is going to change is A, the angle, and then your I, it's also going to change because your power factor is within that equation. But it's the same formula, same both formulas, it's just going to change your EAF because it changes your current. You don't have to switch anything about the circuit, really simple. All you got to do, like I said, is know this, know the reference, and then just know literally one equation. So if you guys could do that, easy peasy. All right, on to homework question numero dos. So we're using the same problem as 5.7, same voltage, but now it's through a feeder with the reactive impedance XF of 0.95. The motor has the same output power, 40 kilowatts. We're ignoring losses still, so we know R is 0. And we have to calculate the magnitude and the phase angle of the line to neutral generated voltage, EAF, which is what we did last time, the field current, IF, but now there's a new calculation, which is the line to line motor terminal voltage, VA. All right, so we have to figure out what the equivalent circuit's going to look like. It's the same as it was before, so we still know that the current is going to be in terms of the motor reference. So just for repetition, this isn't going to be our equivalent circuit, but we know that current is going towards the generation side. So basically, we're going to take, or we'll draw the equivalent circuit. We'll start off with. So it is going to be the same exact thing as how we start. We have our VA, we have our EAF, we have our RA, we have our JXS. But what did it add? It said it's adding a feeder. The output is going through a feeder with a reactive impedance of XF equals 0.95. Reactive, so we know it's a J, we know it's an X. There's no R. It doesn't say anything about an R, so we just think R is 0. So now we're going to extend this branch. There's going to be no R, just another impedance. And then here we have the feeder voltage. We're going to have JXF. So that's all it is. We're just adding a whole nother separate branch. But notice, it's still all an open circuit. So if we have, this would be technically I2, and this would be I1, well, this is, there's no branch. So there's no separate current, so we still know I1 equals I2, which, makes our lives very easy. So what do we know from the equation that could help us get I? Well, how did we get I last time? We took the output power, and we knew the phase, we didn't know the I, and we knew the power factor. Same thing. Why is it the same thing? It's because it's still an open circuit. We're just adding another impedance. So the impedance is going to change when we have to get to that point. But still, I is just 1. The phase voltage is just going to be your VF, because it's saying that voltage that it's outputting is supplied through a 575 volt through a feeder. So this would be your feeder right here, or your technically feeder branches, and this would be your feeder voltage. So we're trying to find VA, and we're trying to find EAF as well. But that's basically what's given to us at this moment that we found. So, and sorry, the power factor is 0.9. Lagging. Kind of all over the place, this problem. But, okay. So, going to do the same thing. I is going to equal P out over 3 times V phase times the power factor, which we have the same output power, we have the same phasor voltage, and we're going to have a different power factor this time. Well, I could change this for simplicity to VF so nobody gets confused. So we're going to get 44.626. Same thing as we got last time, very similar power factors. So the only thing different with this is the added branch, which is just meant to confuse you, but realistically it's just as easy. So now that we have that, we can solve for EAF. So doing KVL, we have minus EAF minus I times Z total plus VF is going to equal 0. Now going back to what we drew, like I said, there's no branch here, so Z total is just these in series. So all Z total is going to be is JXS plus JXF, which is going to be 0.95 plus what was it? 4.95. 4.65. So Z total is going to equal J 5.6. So now rearranging the EAF equation, so that's just going to be the 575 divided by the square root of 3 minus the I that we got. Sorry, I forgot to get the phase angle, but I'll do that real quick. Is it 0.9? Yep. So you just take the inverse cosine of that. You get 25.84. Remember, it's negative because it's lagging. Multiplied by J 5.6. Multiplied by 5.65. So in this one, our EAF is going to equal 316.77 phase, negative 45.24. I'm just going to make sure I'm correct real quick. Yep. Okay. It's one part of the question. Now, this question is still asking for IF. We remember that EAF equals 1 over the square root of 2 times omega E times IF multiplied by LAF. Rearranging, since we know we have the same things as last time. $316.77 times the square root of 2 over 2 pi times 60 times 105 times 10 to the negative third. LAF still hasn't changed, and the frequency still hasn't changed, so we're using them from the previous problem. So our IF is going to give us 11.32 amps. So this question is asking one more thing. This question is asking us to find VA. So we have all of this now. We just don't have VA. So you could do KVL this way. You could do KVL this way. I'm going to do this way because it has one less resistance. Or it's the same resistance because RA is 0. But I mean, do whatever you please. This has a reference angle of 0, so it's less reference angles. So it's basically just going to be minus VA. That's going to be minus I angle times JXF plus VF. It's going to equal 0. So it's basically going to be VA equals VF minus I phase angle times JXF. Or in this equation, JXF was just 0.95. So VA is going to equal VF. VA is, 575 over the square root of 3 minus the current that we got originally, not the field current. The field current is something separate. This current right here, which is 44.626. Same phase angle did not change. Multiply that by J of 0.95. Your VAN, because we're using our phasor voltage, so our VAN is going to be 315.81 phase of negative 6.94 degrees. But this isn't right. He's specifically asking for the line-to-line VA. This is line to neutral. So how do we fix that? Just slap on a square root of 3. So the total VA is just going to be 315.81 times the square root of 3. It's going to be 546, rounded to 547. And then the phase angle is going to stay the same. And that's the answer. So to recap that question as well, basically, same thing, but we add the feeder impedance, which added a feeder voltage. So basically, previously we treated the VA as the open, now we're treating the VF as an open. We solve via KVL around the loop. We solve for I, and we get EAF. Once we get EAF, we're able to solve for our IF via this equation. Once we get our IF, IF that has nothing to do with this, but I was just going in order. Basically, you use a smaller KVL to find your VAN. Like I said, you either go this way, or you could either go this way. Doesn't matter. But you will get this answer. So hopefully this is helpful. Good luck studying.